Properties of limits. Sometimes it's necessary to teach things that are common sense just so we can formalize those things. So let's do that. Let's make a big gap here because I think I want to explain some stuff in the middle, but I want to jump to the end first. So is it okay for me to plug a 3 in straight here, here, here? Well, not here, but is direct substitution okay? Yes. Direct substitution is perfectly fine. It is perfectly acceptable, and I'm going to do that. And I have 3 cubed plus 3 and then plus 5, which of course is going to give me 27 plus 3, so 35 is what I have. There's my answer, but let's step into the middle and formalize a few things. Here's what just happened. I found the limit as x approaches 3 for x cubed. And I ended up saying, well, I can just plug a 3 straight in. I get 3 cubed. Okay, fine. Well, I also found the limit as x approaches 3 for just plain old x, and I was able to plug it straight in, and I got a 3. And I also found the limit as x approaches 3 for 5, and I would say I plugged it straight in, but there are no x's here, so it's just 5, and I got this. So we just talked about the properties of limits on a very basic scale using just a little bit of stuff that was kind of common sense, and we're going to expound on that idea some. So some basic limits. B, C, and N are all constants, and if I approach C, limit as x approaches C for x to some n, some constant value, just like we did here when we had x to the third, just plug the number straight in. So I'm going to have C to the n power. I would just plug that in, okay? If I find the limit as x approaches C for some x value, which I just did, I just get C. And if I'm approaching C for some B, some constant, okay, B and C, and they're all constants, this is not an x, it's a constant, just like this 5 right here was a constant. And I would love to plug a 3 in, but plug the 3 in where? I can't. So the answer is just, well, it's B. That's it. So this next big portion is where we formalize a lot of this with some formulas, a whole lot of writing, and it's going to look a little ridiculous. At first, it's going to be super common sense, and then when we get to the very last one, things change quite a bit. So just bear with me for a moment. If I have a scalar multiple, then I could have the multiple here. So the limit is x approaches C of some b value, some number, times the function. What I really have is b times the limit as x approaches C of f of x. And because they have, within this box, defined the limit as x approaches C for f of x to equal L, capital L, that is the limit, then what I really have is b times L. Okay, here's really what just happened. We just said if I have a coefficient, I could just multiply the whole limit by that coefficient. All right, let's keep moving. Handwriting here was terrible. I should have aligned this better. The L sagged down a little bit. If I am adding or subtracting, not at the same time, okay, this is not plus or minus. This is, maybe I'm adding, maybe I'm subtracting. This isn't like I'm taking a square root and I explore all my options, okay? But if I am adding or subtracting limits, it's the same thing as if I'm adding or subtracting the limits of those individual functions. Okay, so adding or subtracting these two functions is the same as adding or subtracting these limits here. The limit of adding or subtracting two functions is the same as adding or subtracting the limits of the functions, and this one was defined as L and this one was defined as K, so I could just add or subtract those answers. And again, we did this, it seems common sense, and it is. We did the same thing right here. Well, all three of them. Okay, the product, you can see where this is going. This is the same as if I was to multiply x approaches C of f of x times the limit as x approaches C of g of x, and I just have L times K. Let's keep moving because this can get a little bit slow if we just start talking too much about the things that are common sense. Okay, there's this one, g of x, and this is equal to L over K. And one extra little thing on this, you cannot divide by 0. I've tried. This is only true if k is not equal to 0. And then if we raise something to a power, which we actually had that right there. If we raise something to a power, then it is the same thing as raising the entire limit to that power. To the n, oops, there we go. And that would be like L to the n. Okay, now we get to the last one, and this one is incredibly tricky. There are a lot of exceptions to this, or a lot of different things to explore, not so much exceptions, but a lot of different things that we should explore in this one. Oops, excuse me. All right. It's going to be a little wordy, and there's an entire set of practice problems that are dedicated to this idea. So if you're looking back through your notes and you come across this one and you're like, I don't understand that, look at the practice problems because they explore all the nuances of it. Okay, this is f of the limit as x approaches c of g of x. All right, pause that thought for a second. We're taking the limit of a composite function. So what we're going to do is actually find the limit of the inner function and use that for the outer function, but that's if f is continuous and we'll talk about what it means for a function to be continuous. Continuity is an issue we'll deal with later, but you'll see what I mean. If it's continuous at that specific output for the limit of the g function. And then I'm going to put dot, dot, dot. I'd gotten this from looking at textbooks and just trying to formalize this as best as I could, but I'm going to put a little exception here by saying with some exceptions. And what are those exceptions? We will explore those in a separate set of problems.